And that's why it depends on the frame. In one frame, you will see this is electric field, in the other frame, you will see it is a magnetic field. So there is no magnetic field, but it is just a matter of reference. So from here, means Einstein got the clue from here, and he said about the speed of light, another thing, very extraordinary thing. And he published his paper on the electrodynamics of moving bodies. The electrodynamics of moving bodies means he discussed their electrodynamics. He published his work in 1905 and he got a PhD degree here on this one. There were, you can say, then some situations like the special theory of relativity not only say this thing, the speed of light is constant irrespective of the motion of observer or source. It also discussed the length contraction because the length contraction is occurring due to the motion, is due to the frame which is in motion. Or he discussed the time dilation. He discussed the phenomenon of simultaneity, that how that synchronization is disturbed. Then some issues came in with the special theory of relativity, and those were actually not the issues, but the wrong application of the special theory of relativity, like the one we call is twin paradox. Now it is not even a paradox, because we usually say that in twin paradox, two twins, one stays on the earth and the other goes into the space shuttle, and when he comes back, one is celebrating the 35th birthday and the other is celebrating the 40th birthday. The one who is on the cloud is celebrating 40th birthday, while the one who was in the space when comes, he is celebrating 35th birthday. So why the 5 years gap or something like that is occurring? So this is not a paradox. This is actually the wrong application of the special theory of relativity. Like what we consider A will be equal to 0 in special theory of relativity. Now let's consider the space shuttle. This person, this twin is getting in, then this will accelerate. And when it will accelerate, means it is not the acceleration equal to 0 situation. When he will reach the turning point, he will turn, and means the shuttle will turn, and this is acceleration. And then accelerating further, and then decelerating here and dropping in here. So this 5 years will be passed in that one. So both will be celebrating 40th birthdays. The issue was the wrong application. On special theory is for the acceleration equal to 0 situation. And we applied the acceleration non-zero situation, and that's why the theory gave the wrong result. So it was the problem of the wrong application, not of the theory. And when we say that the length contraction or time dilation, this we will discuss more in detail, but this is the introductory lecture, so I will discuss them as well. That length contraction means length contracts from its usual. In one frame it will be certain length, in another frame it will be another length. time dilation. Time will not be the same for one observer and the other observer. It will be different. Moving frame, the clock will tick slower, while the frame which will be at rest, then it will be different. Think of the situation, and the situation is this one. The Newton's zeroth law of motion. The Newton's zeroth law of motion says what? That there is no absolute rest. Everything is in motion. There is no absolute rest. Now let's say I am traveling on the motorway at 1 kilometer per hour, which is the maximum allowed speed. And the motorway police finds me due to the reason that I am traveling at 130 kilometer per hour. But then I say to them that I was traveling at 120, but you were traveling towards me at 10 kilometer per hour. Because you were not stationary. So you are traveling to me at 10 kilometers per hour. That's why you observed my speed like this, while my speed was this. Then, if for example, we just, you can say, then start searching for a stationary person. And there is a person, and he says that no, I was traveling at 115 kilometers per hour. But the motorway police say that actually you were traveling on your bike at 5 kilometers per hour in my direction. Like I'm traveling in this direction and he is traveling in this direction. Yes. So to him my speed is 115, not 120. Every frame in which the observer is considered himself or herself at rest, while the other frames are moving. Why we observe ourselves in motion due to our surrounding. The floor on which I am moving, so due to this I am feeling that I am in motion. I am feeling I am in motion because some air I am crossing, and that gives me the feeling of motion. The surrounding gives me a feeling of motion, like the trees outside, they are stationary and I am moving. Now consider a space where you are having no surrounding, where you are not walking on a ground. How you will come to know you are moving? Means you will consider yourself stationary. And you will consider everything else in motion. So if something is coming to you, it seems it's coming to you, and it may be you who are going there. Like we observe that the sun is rising and falling, but it is actually the earth which goes around it. We see that the moon is rising and falling, but if you are on the moon, you will see that the earth is rising and falling, because wherever you are, in whichever frame you are, you will consider yourself stationary, and rest of the things will be moving with respect to you. So he said there is no absolute rest. Everything is in motion. When everything is in motion, and here we said that all these things are due to motion. Because in motion things will be different. And when everything is in motion, how they will agree on a given length? Length means here space. And how they will agree on a time? Time is time. So how they will agree on both these? Means like we are not agreeing here what is my speed. Motorway police is not accepting my speed to be 120. They say it is 130. Another person is saying 115. When there will be no stationary observer there, everything is in motion, then who will say what my motion is? And special theory of relativity solved this issue as well. It gave you a standard length and a standard time. That is standard, so it is irrespective of the motion. And that was one of the success of the special theory of relativity. The length it gives, every frame will agree with it, whatever the motion of that frame will be. And what that frame will utilize, that frame will utilize the speed of light. And we will discuss that thing further in detail. But what actually Einstein said, that you consider the space-time fabric, it is completely flat, like acceleration is zero. When acceleration will be non-zero, it will have some curvature. So the acceleration equal to zero frame, which we also call as the Minkowski space, that is completely flat. On this flat surface, if a body exceeds the speed of light, trying to exceed the speed of light, then the space no more remains static, but it is responsive. It stretches itself. The space stretches itself, and keeping the c is c, keeping the speed equal to c. If the speed of light is reducing its value, then it contracts itself in order to keep its speed the same. So I hope that after this introduction, we will, from the next class, we will start with the very basics of relativity. Like we will start from the inertial frame. We will discuss all these things: the space-time combination, the length contraction and time dilation, the twin paradox, and the phenomenon of simultaneity, the twin paradox, and all the aspects of special theory of relativity. And then we will include the acceleration equal to non-zero case, which is the non-inertial frame. And Einstein himself took 10 years to include this thing. In 1912, he presented general theory of relativity, but it was not complete. There were so many issues with it. So he spent so he spent 3 more years, and in 1905 he just was successful in publishing the general theory of relativity, and which was giving 16 equations. Out of the 16 equations of the general theory of relativity, 6 equations were identical and only 10 equations. And it took 10 years to solve those equations of the general theory of relativity. And whomever was solving those equations, they were singularity based, so different assumptions of the singularity, like Schwarzschild, he solved the equations, and he coined for the first time the concept of black hole, a singularity. And he discussed with Einstein, but Einstein said that your mathematics is very strong, but your physics is not. And he was not accepting the solution. And it was until 1938, almost 25 years after the theory, two German scientists proved to Einstein like 2 plus 2 equal to 4, that either your theory is wrong or the solutions are right. And then he, for the first time, accepted the black hole concept, that yes, it's a singularity and the black hole are there. And in the morning in the newspaper it came in that the stubborn father accepts his child. So it was Einstein himself took 25 years in accepting the solution of his own theory. And then the scientific community took exactly 100 years to 1915 to 2015, exactly after 100 years, they confirmed the general theory of relativity. Although some experimental confirmation started from 1972, with the help of the Hubble telescope, there were some observations, but the final observation or confirmation came in the form of gravitational waves in 2015. So when we will go to the general theory of relativity, we will discuss all this history and all, you can say, the solutions. And I hope that you will enjoy this course. We are starting from the basics, but here some more, you can say, mathematics, just to get the idea from where the relativity started. Thank you, and stay tuned for the next lectures.